Good afternoon and welcome to the second half of this session on structural materials. And I'm very pleased to introduce our first speaker, Zhenzhu Li, who is now a postdoc in Yonsei University. And she's going to talk about evolutionary exploration of polytypism in lead halide perovskites. So please start when you're ready.
Okay, thank you. Thank you for the introduction. So my topic is evolutionary exploration of polytypism in lead halide perovskite. Then today I will cover three aspects. One is the brief history of the polytypes, and the second part is our methods and the results, and finally is the conclusion and the outlook. So polytypism refers to a variant of polymorphism of polytypes with the same chemical formula, but only the stacking sequence along one axis vary from one polytype to another, leading to different crystal structures. The polytypism of halide perovskite is the result of different stacking sequences of the octahedral layer. So a pair of octahedral can be corner sharing, which exists in the cubic phase, and also denoted as C here. And they can also be fast sharing, which exists in the hexagonal phase, and denoted as H here. And also the hexagonal phase is the undesirable competing phase for when synthesizing the cubic perovskite as photovoltaic materials. And the mix of H and C will lead to the various different polytypes. For example, the HC stacking 4H phase or the HCC stacking 6H phase. And my pointer. Okay. And the polytypes in halide perovskite are now being gradually observed and investigated in more and more research. And actually, in history, the polytypes of oxides are also under active investigation. For example, in this work here, the author finds a very high oxide ion and a proton conductivity in the oxide polytypism. The polytypism is the result of the very small energetic difference between different arrangements. So very similarly in the halide perovskites, due to the energetically favorable stacking of different stackings, there are also some experimental results. For example, here in this work, the coexistence of cubic and the hexagonal phase was characterized under the in-situ optical microscopy in this work. And the author here proposed the amorphous interfacial layer with octahedrals distorted and tilted. There are also very recent works on this site. This very recent work, they synthesize the Ma and Fa lead iodide perovskites, and with characterization evidencing the existence of the 2H interlayer here. And also in this work, the author synthesized the different polytypes of the Fa lead halide polytypes, and different polytypes choose different colors. Actually, the existence of the stacking force in such polytypes will modify their carrier behaviors in such materials. For example, in this material, the lifetime of carriers was dramatically decreased due to the existence of the 2H interlayer phase. And also in our previous work, we also find the hole block and the electron trap in this 3C8H CCM lead iodide polytype. So to investigate the polytypes will be very meaningful because they offer us a platform to investigate the carrier behaviors in such materials. But the first thing for the polytypism in halide perovskite we care about is their energetics. regarding their ground state structure, and low energy structures. Actually, the DFT computed energy for their hexagonal and cubic phase is that for the hexagonal Fa iodide, it's only 70 millieV per layer lower in energy uh, than the cubic phase. And for the iodide, cesium lead iodide, it's 90 millieV per layer lower in energy. But for the cesium lead bromide, the hexagonal phase is 40 millieV per layer higher in energy at 0K than the cubic phase, which means that the 3C phase is naturally the lowest energy state for the cesium lead bromide. And also, as explained before, the different combination of the stacking sequence will, for an n-layer polytype, will be as many as 2 to its nth power. But I will explain later. The real number is far less than this value. So considering the small energy difference and also some experimental findings, the questions we want to answer is firstly, what is the exact stacking sequences that are thermodynamically favorable, and is there any intrinsic common feature of such polytypism? So under this motivation, we use the cesium-lead halide perovskite as the model system to investigate the polytypism of halide perovskite. Here are the representative polytypes with periodicity from 2 layer to 12 layer. And firstly, we defined an ordering energy. The ordering energy refers to the energy difference of a random state polytype um, with its ground state structure. So through our DFT calculation, we find that for cesium lead iodide, the ground state structure is the 2H phase, but for the cesium lead bromide, it's the 3 phase. However, when we see the ordering energy from the model energy, the model ordering energy for both halides shows the same trend and pointing to the 3C phase as the most stable phase for them. But model energy is based on the point charge. So this means for our system-laid halide systems, they are beyond the regime of point charge due to the polarization of the ions. And also we find that the energy difference between 2H and 3C phase of the model energy for both halides are around 2.5 eV. However, they are only less than 100 millieV while using DFT calculation. So it means the Baer-Coulombic interaction are dramatically regulated and screened by the polarization of the ions. And also, the reverse stability trend for both halides shows that the non-negligible role of the anions in these perovskite structures. While using DFT calculation, we can get the reliable energies for different polytypes, but they only limited to relatively small stacking sequences, and it only can provide us with very fragmented picture of the physics of ordering. So considering the binary nature of the stacking sequence, we are the Ising type model Hamiltonian can be built to evaluate the stacking, the ordering energy, and the total energy for different polytypes. As shown in the second panel, we can see that the Ising type model can give a very high fitting accuracy, and with the largest error for the ordering energy being only 3 millieV per layer. Actually, the model Hamiltonian can not only be used to compute the total energy for any random stacking sequence, it also implicitly includes a full set of chemical interactions between different neighboring layers, manifested by a series of interaction parameters and like the interaction coefficients and their corresponding correlation functions here. So for both halides, we have the model Hamiltonian here. And to briefly explain one parameter, H0. So H0 denotes the energy for suspending the monolayer without any interlayer interaction. As we can see here, the H0 for CCM-laid bromide is smaller than the H0 for the iodides, which means that when we have bromide in the octahedral, it's intrinsically more stable than when we have the iodine in the octahedral, which is also inconsistent with their tolerance factor, that CCM-lead bromide has more ideal tolerance factor than the CCM-lead iodide. In principle, with these Hamiltonians, we can calculate the energy for any polytypes we want. But if we want to find out the low energy polytypes, we need to traverse all the candidate space. So is there a way that we don't have to do this? Yes. Fortunately, we have the evolutionary algorithm. An evolutionary algorithm is based on three operations: selection, crossover, and mutation. Selection means to select the elite from the parent's generation, and crossover means to take both genes from the parents to generate a new sequence of gene, and the mutation means the flip, a random flip at a random site. So with the evolutionary algorithm, by choosing the elites during every iteration, the algorithm can efficiently find out the optimum gene sequences that adapt to a given situation. So the central idea for using evolutionary algorithm in our polytype system is the same. Here, our objective is to find the minimum of our model Hamiltonians. This is how it's really working. Firstly, we will choose a random set of initial generation, and they are sorted with respect to the values of their objective function. By selecting the elites and also apply the crossover and the mutation, we have a new generation. This new generation will also be evaluated with the objective function and enter the next iteration until it reaches the convergence. So we can use these parameters to control the efficiency of this evolutionary algorithm. Actually, the evolutionary algorithm works quite well. In our system, the evolutionary algorithm can find the uh, lowest energy structure or the highest energy structure in only 2 and 3 seconds. For CCM-led iodide, we find that the ground state sequence is always the 2H phase, which is inconsistent with our DFT calculated readouts. Except the ground state sequence, we also care about the low energy sequences, which are also experimentally accessible and are highly detectable in the experimental samples. How can we find these low energy sequences? The way is to tune the parameters for the algorithm to have them converge to less perfect solutions for the objective function. Then we can reach the low energy sequences here. Considering the thermal energy at
Zhenzhu, you need to wrap up to stick to time if you don't mind.
okay, so considering the thermal energy, uh, if the thermal energy at the room temperature, if a polytype with the ordinary energy smaller than this number, then it will be shown in the, it will be highly expected in the experiment. And also we find that there are some extremely high energy sequences which related to the intrinsic features for the polytypism. So first, we find that the distinct arrangement for polytypes is much smaller than the 2 to its nth power because of the periodicity of the lattice. So let's take a look at the 12th layer. The total number of distinct arrangements is shrunk by over 19%. Another feature for the polytypes is their symmetrically forbidden sequences, which is the result of the mismatch between the different counts of the H and the C layers. And then we also give the following rules to determine the minimum periodicity of the layer number for different stacking sequences. And then this is pretty much I'm going to talk about today. Here's the conclusion and outlook. And I will thank Professor Aaron and Ji-Sung Park for their discussion, and also thank Help for the chance to, and also the Archer team for the computation, and the National Research Foundation of Korea for their support. And thank you all for listening. Thank you.
Thank you, Zhenzhu. Do we have any questions? So this is quite far from my own area of research, but I was wondering if you could explain what is the Madelung energy?
Madelung energy is the energy just calculates the Coulombic interaction of different ions. So for the real ionic solid, the Madelung energy will be very near the total energy. But if there is there's deviation from the ionic criteria, then the Madelung energy won't be so near to the real total energy.
Thank you. I'm sorry, I don't think noise is coming from my computer. There's a beeping noise. I'm not sure. Sorry. Thank you. I was worried that something had gone wrong, but it obviously was your alarm. Thank you very much. I think at this point it's almost 3:20. So I think what we should do is move to the next talk, which is by Marcus Hurst, and then if we have time at the end, we can have some general discussion. So thank you very much for your very interesting presentation. And Marcus is speaking to us from the University of Surrey. And Marcus, if you don't mind sharing screens, we can share.
Sure. Let me just go ahead and do that. Hold on a second.
And I think you're talking about simulation charring of Phenol-Formaldehyde resins with reactive molecular dynamics.
Yes. Oh no, hold on.
I can't see your slides yet, Marcus.
It's hold on a sec. There's some kind of security problem with it. 2 seconds.
Okay, so hopefully Marcus will come back in a minute, and I'll just ask everyone in the audience to bear with us. Marcus is back. Hi, Marcus. We lost you for a second.
Yes. So now I want to. Okay.
Marcus, I can see your cover slide very clearly, and please start whenever you're ready, and note that it's about 15 minutes to allow some time for Q&A.
Sure. Okay. So thanks very much for obviously inviting me to speak at the conference. So I've been enjoying it so far. I've been enjoying seeing everyone's talks. And today I'm obviously going to talk to you about simulating the charring of phenol-formaldehyde resins with reactive molecular dynamics. So first of all, what are phenol-formaldehyde resins? Well, they are actually one of the oldest commercially produced classes of polymer resin. You probably know them as Bakelite. They have all sorts of applications industrially, including things like adhesives and coatings. But I think one of the most interesting applications they actually have is use in thermal protection systems of spacecraft. So obviously when you have a spacecraft re-entering to the Earth's atmosphere, it's traveling very quickly and you have a lot of gas built up in front of it, and that gas is heated up to a very high temperature. So you need a system in place to protect the astronauts in the space capsule from those high temperatures. And so one of the ways that you can do this is to use what's called a charring ablative material, which phenolic resins work well as. And how they essentially work is that when you heat them up, they give off a lot of pyrolysis gases, and these gases carry away the temperature or the gained heat, and obviously keep the capsule at cooler temperatures. So obviously there was lots of interest in this class of compounds back during the space race, but now obviously there's renewed interest with people like Jeff Bezos and Elon Musk wanting to travel into space. So what's reactive molecular dynamics? Well, with traditional molecular dynamics force fields, you obviously have explicitly defined bonds and bond orders. They have harmonic character and they're parameterized, but the bond orders can't change. So with reactive molecular dynamics, bond orders can change because they're a function of the environment of the atom and the interatomic distance. So throughout the simulation, you can have bonds being created and broken, which is obviously very useful if you want to model any process where a lot of chemical reactions are taking place. So how do we build our phenol-formaldehyde structures to pyrolyze? Well, there's no reactive molecular dynamics force field for resin curing, so instead we use something called pseudoreactions. So we fill a simulation box with phenol and formaldehyde, and then we use probabilities and various other mechanisms to essentially fake a reaction. So just replacing atoms, but obviously done in such a way that it attempts to realistically accurately model the chemical reactions that occur during curing. And as you can see, these methylene bridges are built. You first get a reaction, you get a phenol-methylol group, and then you get another reaction, which is an elimination, and you get a methylene bridge and a water molecule formed. So here's an example of a small structure that's generated using this method. You can obviously see that there are both linear and cross-linked chains here. That's a phenol-formaldehyde ratio. That's a 1.5 ratio. So why do we need to remove products? Well, obviously, as you pyrolyze these materials, they generate a lot of small inert pyrolysis gases. But if you don't remove them, then the internal pressures inside your simulation box start to rise very rapidly as the gases build up in the structure. This tends to impact the formation of large carbon clusters. And it's also more computationally expensive because you have a huge amount of interactions to be computing at every time step. So yeah, high pressure environments hinder the atomization and also the graphitization processes that occur as the charring progresses. So some work has been done on this before, but we wanted to develop a fully automated gas removal script. So previously this has been done with some intervention from people running a script periodically, but obviously that's a very time inefficient way of doing things. And it was just using distance testing, which obviously isn't very accurate. Given that we have this bonding data from Reactive, we should make use of that when deciding which atoms are connected together in molecules. We also obviously wanted something that was generated good data for us and would obviously be expandable code for use with other systems potentially in the future. So just a very quick overview of the software. We built LAMPS as a shared library with a Python wrapper. Parallelization is handled by Python, and this means that we get in situ access to the time average connection tables and in situ removal of products. The problem with continuously restarting and stopping the simulation is that you have to write the data out and then put it back in, and there's inevitably going to be some loss of accuracy during these processes. So here's a quick flow chart showing exactly how the script works. So obviously we initialize lamps on our high-performance computer. We read in our inputs. First of all, we have to equilibrate our sample. So we start at 300 Kelvin, and then we raise the temperature slowly to the target temperature in a sweep over about 10 picoseconds. We tended to find that if you just immediately added a lot of temperature, that the model would just fragment into atoms, which is unrealistic. Whereas if you ramp the temperature slowly, instead you got a convergence of the amount of fragmentation that was occurring. So once we're fully equilibrated, we then run a certain number of cycles, and inside each cycle we'll run MVT dynamics for a certain number of time steps. And at the end of that, we will pull our data out of lamps, identify molecules and determine species, and then delete all the atoms in our target species. And after we've run these cycles, we sweep the temperature back down to 300 Kelvin and output our charge structure. So we had to choose an interval, first of all, to actually remove our products. We wanted to balance maximal acceleration of the charring, but we also needed to allow time for species to form. So we tried runs at various different time steps. And we found that 10,000 time steps was long enough to allow hydrogen dissociation and subsequent forward reactions. But the longer cycles didn't really affect species formation significantly, but they did slow charring quite a lot. Here's some supplementary data. I've included monatomic hydrogen formation from dissociation here. You can see that at very low removal intervals, or very short removal intervals, sorry, that a lot of things don't seem to have much time to form, especially CO2 and dihydrogen. And there's a lot of free monatomic hydrogen that hasn't been able to take part in forward reactions. We also wanted to check for size effects with our models. This has been talked about a little bit in the literature before with coal pyrolysis. So we tried structure sizes at 1,000, 3,000, and 9,000 atoms. We found that the small models had a lot more noise in the data that they generated out from them, and they were less able to show trends in things like, we're using mass loss here as a representative example, but this occurs for most of the other things as well. So having a larger model is better. I don't think that these are fully converged, but this is a testing phase, so we wanted to use smaller models just so that we could run the simulations a little bit faster. So obviously we achieved the goals of our development with our fully automated code, and we had in situ identification and removal of molecules. We were able to accelerate the charring a lot. We achieved fully charged 98% carbon structures within 250 hours of time on our high-performance computer using 24 CPU cores. That was for a 10,000 atom model. And for reference, with no removal, 600 hours of CPU time yielded no large carbon clusters. Here's a quick video of the trajectory. You can see that obviously at the beginning you have a lot of complex reactions and a lot of fragmentation, but as the pyrolysis process is progressing, the carbon clusters are starting to agglomerate together and rearrange, and you get a lot more formation of 5, 6, and 7-membered rings, but particularly 6-membered rings. And you can see that the carbon is arranging itself into graphitic sheets that are actually stacked on top of one another. And one thing to note here is that we wanted to check whether or not this happened if you just put a lot of carbon atoms, into the simulation box. We wanted to make sure that they weren't just going to do exactly the same thing, no matter what the process. But it turns out that if you do that, you get something that looks a lot more like amorphous carbon with a lot of sp3 carbon. These carbon sheets are formed more from a very slow deposition of carbon atoms. So pyrolysis seemed to go in a very predictable way in all of our simulations. You had the initial loss of volatiles and water. You started to get the dissociation of some hydrogen atoms within the structure and the reaction of phenolic hydroxyls with other parts of the structure. After this, we started to note the breaking of methylene bridges and ring openings. These varied at different temperatures. And once the ring openings started to occur, this really seemed to rapidly increase the amount of fragmentation and atomization of the structure. So you've got a lot of more complex reactions between fragments at this point. As the gases are removed, you get voids in the structure that appear, and these voids seem to further promote the formation of new pyrolysis products. So it becomes a runaway cycle where the more gases are removed, the more form, until you eventually just get left with carbon clusters, which will reagglomerate. Here's just another quick overview of the pyrolysis process. You can obviously, again, demonstrated here how in the beginning, you obviously have a lot of oxygen in the structure, and you start to form these long kind of filaments of carbon, as well as small clusters. And it's these filaments and clusters that recombine with one another to form the graphitic sheets. And obviously by the end, they've all recombined. So we tried pyrolysis at various different temperatures, 1,500 Kelvin, 2,500 Kelvin, and 3,000, just to see how this affected the process, because we had read in the literature before that reactive F tends to underestimate the amount of, or overestimate, sorry, the amount of energy needed to push these reactions forward. So first we'll come to our carbon cluster formation for our various different models. So I think one interesting thing that's very apparent here is that with low formaldehyde to phenol ratios, methylene bridge breaking is very obvious. You can obviously see that you form regular sized fragments, which equate to repeat units from the polymer. And this is obviously much less apparent at higher temperatures. The other thing that you can notice here is that ring openings, which are leading to fragmentation, are more apparent at higher temperatures, because you get more of a continuum of cluster sizes. And then obviously you see that most of the clusters are disappearing as they all combine back together towards the end of the simulation. Most of the activity seems to occur within about the first 100 picoseconds. So here's graphs of ring formation for each of our 9 simulations as well. Again, you can see it's very obvious that obviously in the beginning you're getting ring openings for of your 6-membered rings that start off in the initial structure. You can see at low temperatures at 1,500 Kelvin, with a phenol to formaldehyde ratio of 1, you see a lot more ring opening than you do at 1.5 or 2, but at higher temperatures this seems to make less of a difference. Once most of the initial rings have opened, you then start to see the number of 6-membered rings rising again, and obviously this directly relates to the formation of the graphitic sheets. One interesting thing to note is that at 3,500 Kelvin, you get a lot of 3-membered rings early on. And from observing and kind of investigating the structures, we see that there's a lot of epoxide formation during that first 100 picoseconds. And this tends to tail off, obviously, as the oxygen content decreased. Some of that is also from 3-membered cyclopropane rings. Here's elemental compositions, again demonstrating how at lower temperatures some oxygen is never completely removed from the structure during the first 2 peak seconds. As you go to 2,500 Kelvin, all of the oxygen is removed, but the hydrogen remains, and only at 3,500 Kelvin is all of the hydrogen removed. We've also got char yields graphed down the side here, and obviously you see that higher temperatures give lower char yields, and obviously a phenol-formaldehyde ratio of 1 gives a lower char yield as well than more highly cross-linked structures. So here's stack plots of pyrolysis gas evolution. Dihydrogen seems to always be a major product from pyrolysis, which is backed up with experimental results in the literature. You also see that C2H2 increases significantly at higher temperatures, and it also seems to be linked to ring formation, which is again kind of evident here in that you can see that acetylene is forming more readily with a phenol-formaldehyde ratio of 1 at 1500 Kelvin when ring opening was higher. So obviously greater volume of products is formed as the temperature is increased, and most things are lost during the initial few picoseconds. Many small complex structures are found early on. You get a wide variety of different fragments, but by the end of the simulation, everything is pretty much either hydrogen or small or large carbon clusters. So the complex reaction mechanisms are really only taking place when oxygen is present. We also came up with a simple kinetic model with 6 major reaction paths investigated. We found that dissociation of hydrogen and reaction of phenolic hydroxyl are primarily drivers of thermal decomposition. Decreased oxygen content seemed to lower the rate of mass loss, which would make sense given this. And also acetylene formation reactions also seem to accelerate pyrolysis, which we see from the ring forming. It's interesting to note that the amount of water and carbon dioxide formed at higher temperatures actually decreases. This could be because those reaction pathways are less apparent, or because they are taking part in forward reactions. Mass transport, we see primarily thermodynamic control of the initial reactions, but once we start to see more space opening up, we tend to get reactions that are limited by the availability of physical space of fragments. So fragments physically have to move towards each other in order to react. So conclusions. Obviously, we've discovered that LAMMPS is useful for running these reactive F simulations.
Marcus, maybe if you just leave the conclusions up and we can take questions while people read them, because we are heading towards 20 to 4 and we should try to keep on time.
Apologies.
No, you started slightly late, so you don't, no need to apologize. So could I see if anyone has any questions for Marcus? So Marcus, you know, I use LAMMPS in a completely different way to you to simulate systems of granular materials, and our interactions are quite different and very local. And we find we can get about 100 particles per core is where we should be for scaling. And you know, I've actually been kind of batting back and forth a bit with Archer recently on that, because and is it generally accepted that when you're looking at molecular dynamic simulations and simulations with LAMMPS, that you should look at the number of particles per core? Is that something that people typically do? Because we kind of work that out ourselves in isolation.
Yeah, so I actually did investigate this. We discovered that our main problem is that obviously these are quite high energy simulations, so the particles tend to move quite quickly. So we actually had a lot of problems with ghost atoms, which is that if an atom moves outside of its, more than 2 box lengths outside of its processor domain, it tends to get lost. So we actually had to limit the amount of atoms per core. We had to kind of very fine tune that so that we could balance between obviously getting fewer atoms per processor core, but also not having too many lost, or not having any lost atoms. So we were trying to fine tune between those two.
Okay, I don't think we had an issue with lost atoms. I think ours was just communication time. So yeah, but I thought that the material you were talking about in terms of removing atoms was applicable to some of the stuff we do in granular materials, where we look at particle crushing, and we need to get rid of the particles close to the comminution limit, the very small particles, because they dominate the simulation time. So, you know, it's quite a different application for some of the work you've done, but I think it could be transferred into that.
Yeah, I think there's lots of avenues to build upon this and improve this. Obviously, this is still quite in the early stages of development at the moment.
And is using a Python wrapper to run LAMMPS, is that very common?
It's not too uncommon. I know Python anyway, so I found that it was a very intuitive way of performing. Obviously, LAMMPS is fairly limited in the amount of kind of calculations and things you can do in the background. So obviously, being able to take it out and use Python, and then also utilize things like NumPy and other modules is obviously much easier. So I think it is fairly common. You don't get too much of an overhead either from using Python on top of LAMMPS.
Yeah, I think it would solve some problems we've been having with LAMMPS recently. So that was just, you know, kind of on the coding side.
Well, feel free to message me with any kind of question, any more questions you have about it.
Yeah, I may well do. Thank you. Any other questions for Marcus, perhaps more from the chemistry side? Thank you very much for such a clear presentation. And as I said to the last speaker, perhaps you can just hang on to the end of the session in case any questions emerge. And we'll move to the final speaker of the session, who is Andreas Hermann, who's a reader in the University of Edinburgh. So moved from the south of the UK or Great Britain right up to the top. And Andreas is going to talk about electronically driven cooperative diffusion in simple cubic calcium.
Yeah, thank you very much. Right, I guess you can hear me all right and see the screen. So, right, so I'll talk about something slightly different. Simple cubic calcium, but my motivation side will be trying to pretend that we're talking about something else yet again, which is what's the structure of Earth's inner core. And I'll try to convince you that these two things are related. So, as you know, Earth's inner core is solid and is an alloy dominated by iron. But the question is, what is the crystal structure of this alloy, and therefore, what's the crystal structure of the core? So there's various candidates: HCP, FCC, BCC crystal structures. If one looks at the iron phase diagram, as it's known from experiments, they go up to about 200 GPa, so that's about 2 megabars in pressure. And it seems that epsilon iron, which is HCP, seems to be the relevant phase that kind of goes all the way up to the melting line. But the inner core pressure and temperature conditions are somewhere up here, so it's still a way to go. So the question is, what is really there down there? And there's been arguments now made recently that BCC iron should be looked at. So ab initio molecular MD simulations of BCC iron at pressure temperature conditions at the center of the Earth have essentially found certain concerted diffusion processes, which are quite interesting. So here's an animation of the trajectory. So for a while, nothing happens. But if you keep squinting, then you can see stuff moving around a bit. So there's this concerted diffusion of atoms happening. And then it's all BCC again. So if you plot the kind of the time average of this trajectory, then you can see, there's like these atoms move around in these rings or maybe along lines, and maybe they intersect or they go around a corner or not. And it seems to be quite a curious little effect, but it does lower the free energy of BCC iron to the extent that as of the latest calculated phase diagram of iron, there's a big sliver of this BCC phase present in PT space above the HCP phase as a high temperature phase. And that very much crosses this inner core boundary pressure temperature conditions. So this curious little effect here has the potential to change effectively what we think 25% of our planet is made of, if you will. This diffusion is not limited to iron and to very extreme conditions. So it has been seen in other BCC transition metals. So it's been known for quite a while. I'll just show you here some relatively recent results from simulations. So this is classical MD simulations on tantalum, where the people have called it plastic flow, this regime where you get some motion that is not a solid anymore, but clearly not a liquid either. And here's another graph from a simulation on titanium, ambient pressure, high temperature. And so you see as the kind of trajectory is summed up over the simulation, you see atoms moving along lines, moving around in circles, in rings, and so on. So you've got systems that are not solid, but not liquid either, so kind of like coexisting at the atomic level. And it's also known from other systems. So partial melting is at atomistic level is a thing. So you might be familiar with superionicity. So superionic conductors are compounds where usually the light constituents diffuse above a certain temperature, whereas the heavy constituents are solids. So here's a simulation results from Syria. So above 2250 Kelvin, the oxygen starts to diffuse, but the cerium always remains in the crystalline lattice site. Here's a picture from dense water. So hydrogen is hot dense water. Hydrogen can diffuse throughout the entire system, and oxygen forms a crystalline lattice still. So these are compounds, but you also get some exotic kind of partially molten states in pure elements. So some elements, like particularly all alkali metals, but also some others, form host-guest crystal structures under pressure. So these are structures that are made of a single element, but they arrange themselves in two interpenetrating lattices. So here's a picture of well, potassium in this case, but it's the same for all alkalis. So the gray atoms are what we call the host lattice, and the green ones are the guest lattice. They form these chains. And if you look at a simulation of these, then maybe you can see it is a sideways view. You can see these chain atoms wandering out relative to the host lattice. But that's fine. So the lattices can move against each other. But what's interesting is that the correlation between these chain atoms, between these guest atoms, is lost. So if you do a diffraction experiment in that situation, you will not get any diffraction peaks from the chain sublattice, from the guest sublattice, but the host sublattice is still solid. So you have a material that's solid and liquid at the same time at an atomic level. You have got the solid and liquid atoms right next to each other. Right, so that is one thing that can happen, but this is a very complicated crystal structure. It's a very peculiar effect. So now to calcium. So this is a phase diagram of calcium, and there's no peculiar crystal structures in there. On the contrary, so calcium's ground state is FCC lattice, and then under pressure, there's a BCC phase and a high temperature phase BCC as well. And then it goes into a simple cubic phase. So this is the melt line here. So the melt line plateaus out actually. And then as the simple cubic phase arrives, there's a steep increase and then a second plateau. Now, simple cubic phase is interesting because that shouldn't exist. Simple cubic phases should always be elastically unstable. And in fact, there's been theory, and I'll show you more on the next slide, that at low temperatures, the simple cubic phase the symmetry should be broken, and there should be some lower symmetry phases present instead. But a lot of experiments have confirmed that simple cubic calcium is a thing at room temperature and above. Okay, but as I said, in calculations, this is not seen, at least in the ground state. So if one does a standard harmonic phonon calculation on simple cubic calcium, one gets imaginary phonon modes. So the sign of lattice instabilities, depends a bit. This picture changes a bit depending on pressure, but they're always present. Yeah? So the simple cubic phase is not really stable. And if one follows those imaginary modes towards kind of an energy lowering and symmetry lowering pathways, then one ends up with various lower symmetry phases that are more stable. So here I plot literature results on the enthalpy against pressure. So DFT is this density functional theory, can reproduce FCC being stable in BCC, but then instead of simple cubic, which is this maroon phase here, there's a whole other phases or whatever, some tetragonal phase, orthorhombic phase that come in instead of the cubic phase. And eventually in low temperature experiments, those low symmetry phases were seen. So here's an identification of an orthorhombic phase and possibly the tetragonal phase. But at high temperature, calcium remains simple cubic. And we can understand that as well now if we include anharmonicity in the phonon calculation. So we can renormalize the phonon frequencies by accounting for the finite displacements of the atom at the relevant temperature. And if one does that, one gets the instability goes away, and the material is fully dynamically stable. I'll go more into detail that in a minute. Okay, but these are all low temperature effects. And what we are interested in is the high temperature properties of the simple cubic calcium phase. So we run some ab initio molecular dynamics first to start off with in some supercell using VASP code and some standard settings, and probing temperatures that range from the solid phase to safely above the melting line to see what happens. And we see that, yes, as you increase the temperature, the atoms become diffusive, but they do so at temperatures that are much too low. So already at 1300 Kelvin and above, we see a finite displacement of the atoms after finite runtime. Now, there seems to be a clear distinction here between this kind of intermediate temperature regime and the high temperatures. And it's also reflected to some extent in the phonon densities of state that we extract from the velocity autocorrelation function. So at this intermediate temperature regime, where the displacement is relatively low, relatively small, the phonon density of state still has quite some features, retains features from the solid phases. Whereas at the highest temperatures, there's no features left. So this is possibly, well, fully molten, fully liquid. Okay, so, but what's going on in this intermediate regime? So we looked at it a bit more closely, and here's an example for the mean square displacement of the atoms resolved by crystalline direction. It's not something one usually does, but here it turns out that for that particular simulation, all the displacement happens along the x-axis and none in the y and z axis. Now, it's a cubic system, obviously, simple cubic. There's no reason to prefer one axis over the other, and in other simulations, it goes in another direction. But the principle is like this. And in fact, we can distinguish solid and liquid atoms within the cell. So, and that's this yellow and blue coloring here. Yeah? So the yellow ones are all solid atoms, and we track what they do, and they don't move. They don't get displaced from the lattice sides. The blue ones are, well, the liquid atoms, if you will, and they move a lot, actually. And because they're all aligned along a crystallographic axis, that's where all the displacement happens along one axis. And again, we can pull out the phonon density of states projected onto these atoms, and there's a clear solid-like behavior for the large set of the atoms and the liquid one for the rest. Now, this is a relatively small cell. This is DFT calculation, so this is expensive. And effectively, what we're seeing here is that we have a long chain of atoms. So with periodic boundary conditions, an infinite chain of atoms moving against the backdrop of the rest of the cubic crystal. And that could be an entire, I mean, this is not a realistic motion, so this could be entirely an artifact due to finite system size. So to probe that and possibly get rid of it, we trained a deep neural network interatomic potential on around 7,000 configurations taken from the ab initio molecular dynamics that capture from the solid into the liquid regime at two different pressures. Here are the kind of the training success, if you will, in terms of how the potential can describe the energetics and the forces on the atoms in these configurations. And then we use lamps to do classical molecular dynamics with this. And here I show you the radial distribution function comparing the DFT calculation and the deep MD classical simulations, and you see very good agreement. So structurally, this potential gets it right. And now we can scale up the simulations a lot more. So this is now showing you the trajectory projected from a 15,000 atom calculation. And now you see this behavior of atoms having this concerted motion running along in chains, maybe taking a corner, forming rings, relatively large rings, relatively small rings. You have lines that intersect each other. And it's not a finite size effect. You know? So this behavior is localized within the units, within the supercell. So this is real. This is physical. I'd like to show you here the simulation of the solid, where you see absolutely nothing because everything is on the lattice sides. And here at 1300 Kelvin, you can see now the dynamics. You can see these little snakes of atoms moving around. So everything gets started by a Frankel defect evolving in the system somewhere. So somewhere in this simple cubic lattice, a calcium atom will hop out of the lattice sides, and that will pull along a whole chain of other atoms. But in the end, they will all slot back into the simple cubic crystal structure. So on average, this looks like a solid. If one does diffraction experiments on this will look like a solid, which is probably why it hasn't been detected so far, but it's not. No. Okay. Now, why is this happening? So let's look at the electronic structure of calcium. So simple cubic calcium is what we call an electroide. That is that you have electron localization away from nucleosides. So this is the simple cubic unit cell, and here's a pocket of an electron pair that sits right in the center of the unit cell. So this is something like a pseudo-binary ionic compound. Yeah? So if calcium 2+ on the corner and electron 2- in the center, cesium chloride structure, if you will. Except that the ion in the center is very, very malleable. I mean, it's just a wave packet of electrons. Because the electrons are localized, this structure is actually quite a bad metal. If you look at the electronic density of states in the solid, you see there's a very pronounced pseudo gap around the Fermi energy. And that is also retained in this chain melting, in this diffusive regime, but not in the liquid. So this we can understand because we then went back to our supercell and deliberately moved a chain of atoms along the one crystallographic direction. And so here the isosurface is the electron localization function. So think of this as where it's red, that's where the electrons are. And as we move these atoms along, this is labeled in pink, you see that kind of distorts the electron pocket right next to it, but further on, nothing happens. So there's no effect on the rest of the lattice, no effect on the overall electronic structure. So that also explains why this motion has a very, very low barrier of happening. So here we like I said, we deliberately track a whole chain of atoms as it moves along the lattice from effectively simple cubic back to simple cubic, but with all the atoms having slotted over by one side along various low index directions. And you see that this 1, 0, 0 direction, or equivalently the y and the z directions, have a very low barrier to overcome. In fact, it goes a little bit energetically downhill if you move the atoms away from the high symmetry side. You can't see it on this scale, but the energy goes a little bit down. And that is why the phonons come out imaginary, or this is why there's a dynamic instability, because you can energy gain by moving an atom away from the high symmetry side. And so here are our phonon calculations. And again, so in the ground state, we probe this negative curvature around the lattice side of and so we get an imaginary phonon mode. At a reasonable temperature of 600 K, the atomic displacement will actually probe the repulsive part of this potential well, even though it's very, very little or not very large. But effectively, all the atoms feel a restoring force, and so that the crystal is dynamically stable. All phonon modes are positive. That's the blue line here. But as the temperature increases further, because the barrier is so small, atoms will eventually probe the maximum and will be able to move freely through the crystal. And so at 1200 Kelvin, that mode softens again and reaches 0. And just above that temperature is where diffusion will set in, because there's effectively you have a ground state instability on the lattice that can be overcome or is stabilized by thermal fluctuations. But at high temperature, the instability comes back in because the barrier against the concerted motion is so low. Okay, so overall, we can construct a phase diagram of calcium based on our MD simulations. We find the melting temperature in very good agreement for the BCC phase at low pressure. And then at high pressure, we find a significant increase in the melting line compared to before. So this is all the simulations on the simple cubic phase. And that increase in the melting line is solely due to the emergence of this partially diffusive regime. So there's the green stars here. Actually, it onsets a little bit earlier or a bit lower temperature and higher pressure. So with pressure, this gets easier, but the regime is also longer lived in terms of thermal excitation, and so the melting temperature rises. The experimental curve is up here, so we're not quite getting the slope right, but we're getting the qualitatively very well. Okay, so to summarize what I just told you, I told you a little story about simple cubic calcium, where we uncovered a cooperative diffusion regime at elevated temperatures and pressures using ab initio or machine-learned molecular dynamics simulations. In turn, the presence of this partially molten phase, because it is now has a lower free energy than the pure solid, leads to a marked increase of the melting temperature and explains the melting line behavior of calcium. We can link the presence of this state to the particular electronic structure of calcium, it being an electride, and the emergence of a high temperature dynamic instability as opposed to a ground state dynamic instability. What we've shown then is, or with this, is that cooperative diffusion is not only restricted to BCC metals, it can occur in other crystal structures as well. So it might be a much more general feature than what people think of, and not restricted to high pressure situations either. So what we reckon are indicators for this effect are probably strong lattice anomalisticity as seen in theory calculations, or rapid rises in the melt line that are somewhat unexpected as seen in experiment. And I have to thank my collaborators, Zhenzhu from Nanjing, who has derived and pushed forward this project, and Ariel Tosati from ICTP for his contributions. In our paper, you can look up in PhysFX. And yeah, funders I shall thank for providing money and computing resources. And thank you for your attention.